Welcome to the Deep Dive Books channel, where we hope you find something valuable every day.
Today, we continue discussing Malcolm Gladwell's Revenge of the Tipping Point. This is the fifth part of our interpretation. We're diving deeper into the topic of social engineering. Previously, we explored two mechanisms that trigger the tipping point for trends. One is the small area overstory, and the other is when a minority group within a population exceeds a critical threshold. Today's theme focuses on the third factor, superspreaders. This concept ties back to Gladwell's earlier book, The Tipping Point, where he introduced the law of the few. It posits that trends are often initiated by a small group of individuals. This mechanism remains relevant. It's the power of example. For instance, we previously discussed how a series of student suicides at a high school in Poplar Grove were influenced not only by the monocultural overstory, but also by the high social status of the individuals involved, making them more likely to be imitated. Sometimes, the outbreak of a trend is coincidental, but more often than not, a few superspreaders play a crucial role. This aligns with the well-known 80-20 principle, also called the Pareto principle. The majority of the impact stems from a minority of individuals. While the theme remains the same, the case study in this discussion took me by surprise. Of course, we owe this insight to technological advances and historical opportunities. I sincerely hope that the theories presented in this discussion prove to be correct and gain widespread acceptance, as they have the potential to benefit human society. The case in question is the COVID-19 pandemic. Do you remember the sense of frustration during the pandemic? Perhaps you had this thought. Wouldn't it be wonderful if we had a way to instantly detect whether someone was carrying the virus? Imagine placing such a device at the entrance of every public space. Infected individuals would be barred entry, allowing the majority to resume normal life, and the virus would soon vanish. Some researchers indeed explored the idea of using optical sensors to detect COVID-19. However, coronaviruses are extremely small, with a diameter of only 0.1 microns, making detection highly challenging. But Gladwell's book made me realize that the solution could be much simpler. What you truly need is not to identify who carries the virus, but who spreads it. That's right. A carrier isn't necessarily a spreader. In fact, most carriers are likely not spreaders at all. It's possible that many people are infected, but only a small number actually transmit the virus. Here's the good news. Detecting spreaders might be significantly easier. Let's start from the beginning. We know that COVID-19 was first identified in Wuhan at the end of December 2019. Initially, the rest of the world didn't take it seriously, failing to restrict international flights departing from China. As late as January, a Chinese student flew from Wuhan to Shanghai, then from Shanghai to Paris, and finally to Boston to continue his studies. On January 31st, he was diagnosed with COVID-19 in Boston. Imagine how many people he came into contact with during his journey. 30 hours of flights, airport queues, immigration procedures. Surely, he must have infected many people, right? Actually, no. Although he was a virus carrier, he likely didn't infect anyone. We can make this claim because, by March 2020, scientists had developed the ability to trace the transmission routes of the virus. COVID-19 mutates rapidly, so the genetic makeup of the virus carried by each person isn't identical. By analyzing these genetic variations, scientists can determine who infected whom, and even trace the origin of a specific strain. Within the first few months of the outbreak, 120 individuals brought new virus strains to the Boston metropolitan area. Yet the vast majority of these strains failed to spread. Even when they did, most transmission stopped after 1 or 2 steps. For example, a local nursing home saw nearly all 97 residents infected, with 24 fatalities, and a third of the staff also contracted the virus. Despite this, the outbreak didn't turn the nursing home into a major source of transmission to the outside community. The virus often seemed to reach a dead end, unless it encountered a superspreader. On February 26, 2020, a biotechnology company, called Biogen, held its annual leadership retreat at the Marriott Hotel, in downtown Boston. Over the course of 2 days, 175 executives from around the world convened and then dispersed. A few days later, at least 50 attendees were confirmed sick, and considering asymptomatic cases, the event likely infected over 100 people. These individuals carried the same strain to 29 states across the US as well as to Australia, Sweden, and Slovakia, resulting in a cumulative total of 300,000 infections. The strain itself wasn't special. The key factor was the highly conducive environment of this jet-setting gathering. But why did this particular conference lead to such a massive outbreak, while countless others didn't? Scientists later estimated that a single individual at the event was likely a super spreader. Traditional models of infectious diseases assumed that everyone had roughly the same level of infectiousness. This is clearly not the case. To understand why some people are super spreaders, let's examine how COVID-19 spreads. Until late March 2020, the World Health Organization maintained that COVID-19 spread through respiratory droplets produced by coughing, sneezing, or speaking. Droplets are relatively large and heavy, quickly falling to the ground, so maintaining a certain physical distance was deemed sufficient. This guidance was incorrect. In April 2020, aerosol chemists published a paper suggesting that COVID-19 could spread through aerosols. Aerosols are tiny particles less than 10 microns in diameter, essentially microscopic droplets. Normal breathing produces aerosols, and because they are so small and light, they can remain suspended in the air for over an hour. This means a virus carrier doesn't need to sneeze. Simply being present in a room is enough for the air to become saturated with virus-laden aerosols. Even after the person leaves, the aerosols can linger. This explains how one individual at the Boston conference could infect so many people just by being in the room, without needing to sneeze at each attendee individually. You might wonder why it wasn't until April 2020 that the idea of aerosol transmission of viruses gained traction. This is because aerosol research is primarily conducted by chemists and engineers, while scientists studying viruses are not familiar with such interdisciplinary topics. This highlights the need for more interdisciplinary research in the current era. Simply exhaling produces aerosols, but the amount of aerosols in the exhaled breath of most people is relatively low. However, some individuals exhale significantly higher amounts. In an experiment involving 194 participants, researchers measured the number of aerosols in their exhaled air and found that only 18 of them were super emitters. On average, these individuals exhaled 3,545 aerosols per liter of air, 20 times more than low emitters. If such individuals are infected with a virus, they become super spreaders. Toward the end of the pandemic, a group of brave volunteers deliberately infected themselves with COVID-19. The experiment revealed that 86% of the viral particles were transmitted by just 2 out of 36 participants. In essence, virus transmission is caused by a very small subset of individuals. So, who are these individuals particularly adept at producing aerosols? Current conclusions are only statistically significant, pointing to 3 main groups: older people, obese individuals, and those already infected with a virus. A common feature among these groups is a tendency toward dehydration. When the body is well hydrated, the upper respiratory tract remains moist. Incoming air, even if it contains viruses, is naturally captured by the upper respiratory tract and carried down to the digestive system with saliva, where it is neutralized, posing no risk. However, in a dehydrated state, the upper respiratory tract becomes dry and loses its ability to trap viruses, allowing them to enter the lungs and cause infection. This is why drinking more water during winter, when viruses are more prevalent, is crucial. One key sign of dehydration is thick, sticky saliva. When such individuals speak, their vocal cords generate large amounts of aerosols, spreading them through exhalation. While further research is needed, a simple observation is that individuals with the stickiest saliva are likely the most prolific super spreaders, potentially 20 times more dangerous than the average person. As early as the 1970s, scientists noticed that some individuals had an extraordinary ability to spread viruses. For instance, in one measles outbreak at a primary school, it was initially assumed that students infected each other on the school bus, given the enclosed space. However, it was discovered that most infections were caused by a second-grade girl who had never ridden the bus. Moreover, she infected not just her classmates, but also students in 14 different classrooms. Scholars later hypothesized that the Boston Conference outbreak followed a similar pattern. The virus strain was known to have originated in France, so it was likely brought over by a European attendee, possibly an overweight individual. This person might have avoided drinking water on the long flight to minimize bathroom trips. Obese individuals typically need to drink more water to stay hydrated. Moreover, he might have consumed alcohol, which accelerates dehydration. After breathing dry air for 12 hours on the plane, his upper respiratory tract became extremely dry. By the time the conference began, his saliva had become thick and viscous. He gave a passionate speech with a strong voice, and chatted loudly with others. His aerosols spread throughout the entire hall. If scientists have long been aware of the existence of super spreaders, why hasn't there been systematic research on the subject? Because addressing this topic risks fostering discrimination. If we claim that people who fit criteria 1, 2, and 3 are potential super spreaders, and should be treated differently, wouldn't that lead to stigmatization? No one wants to tackle such an awkward topic. This brings us back to the challenges of social engineering. Should human behavior be managed like an engineering problem? The 80-20 rule, where a small number of sources cause most of the issues, is not limited to people. Over a decade ago, chemists discovered that automobile emissions are not evenly distributed among vehicles. Roughly 10% of cars on the road are responsible for over half the pollution. Addressing just this 10% would significantly alleviate the problem. Currently, many regions mandate annual or biennial vehicle emissions testing for all cars. This not only wastes everyone's time, but also allows the worst polluting cars to cheat the system. There is now a device capable of real-time infrared measurement of vehicle emissions. The best solution would be to eliminate mandatory emissions testing, and instead install these devices on roadsides. Any vehicle caught exceeding limits would be penalized immediately. However, such policies face resistance, because the worst polluting vehicles often belong to low-income individuals. Transitioning from universal measures to targeting specific groups risks accusations of discrimination. Imagine if another coronavirus pandemic occurred. The most effective approach might be to conduct rapid screenings at the entrance of every public venue. Those who are obese, elderly, or have excessively dry saliva could be denied entry. This would make life much easier for society as a whole, but people would accuse such measures of being social engineering. That's it for today's content. Thank you for watching, and I'll see you in the next video.
If you feel there is value in this, please like, subscribe to this channel, and leave your thoughts or suggestions in the comments section. Let's grow together and read more good books.